Welcome back. We're now going to use our unit vector notation to solve a projectile motion problem, and we probably could have solved, actually we definitely could have solved this without the unit vector notation. But what we'll see is when we do it this way, we can do a lot more just kind of not having to draw pictures, and we can actually get a little bit more intuition into what happens with the problem and kind of solve it in a deeper way. So let's start with the problem. So say someone hits a ball that's starting 4 feet off the ground. So let me draw the axes. So that's my y-axis, and we're only going to deal with the first quadrant, so that's all I'll draw. That's y, that's x. And let's say the ball starts off 4 feet off the ground. So that's 4. That's where the ball starts. And what does it say? Hits a ball, okay, say you hit a ball that's 4 feet above the ground with an initial velocity of 120 feet per second. The ball leaves the bat at a 30-degree angle with the horizontal and heads towards a 30-foot fence 350 feet from home plate. Okay, so let's see what this is. So let's draw the velocity vector. 120 feet per second at a 30-degree angle. And this won't be drawn to scale just because I don't have space to draw it to scale. But the velocity vector is going to look something like this. And that, of course, is at a 30-degree angle to the horizontal, right? If this is the horizontal. What does it say? Okay, and it heads towards a 30-foot fence 300 feet from home plate. So 300 feet, I mean 350 feet is going to be way out here. And let's say this line keeps going. This is 350 feet. It's not drawn to scale because if this is 350 feet would be much more than that. But it's a 30-foot fence. The fence is, let's say we're in Boston and it's the Green Monster. And I don't know if that's 30 feet high, but say the fence is, it goes up roughly to 30 feet up there. 30 feet. So that's the fence. And the first question they say is, does the ball clear the fence? So let's see if we can do this using vector notation. So just so we start off with, so we don't get too messy with this problem, because I think I'll run out of space if I did, I'm going to give you an equation, and this equation should make sense to you from the projectile motion problems that we did earlier in physics without using the unit vector notation. And if it doesn't, I'll maybe make another video where I prove this to you. But in general, and everything we did in the projectile motion problems to date, we essentially broke it down into two one-dimensional problems and then solved each of the dimensions. Now we'll keep everything as vectors and solve it all at once. So this is exciting. So let's say P for position. So the position at any point in time, and the position is going to be a vector. The position at any point in time, and this is a good thing. I don't want you to memorize it. I think it should make intuition. It should be intuitive for you, and then especially if you can prove it. And I'll prove it to you in the next video, just in case it doesn't make a ton of sense. Although it should make sense from the projectile motion problems. The position at any given moment in time is equal to the initial position. The initial position, and that's going to be a vector, plus the initial velocity, that's a vector, so I put these little funny arrows on top, times time, plus the acceleration, and of course acceleration is a vector, times time squared over 2. This is a good thing to know, and it's actually even a better thing to be able to prove. So let's see what we can do with these. And what's interesting here is all of these are now vectors. And this would have worked if they weren't vectors, if we were just in a one-dimensional domain. But what's cool now is we can do this in 3 dimensions, or 5 dimensions, or whatever dimensions. So let's see what we know. What's the initial position? So Pi, it equals what? So how much do we move in the x direction? Or what is the multiple times the I vector? Well, we haven't moved at all in this is the initial vector, right? The initial position. So it's only 4 in the y direction, or the 4 times the j vector. So it has no x component, so 0 times I times the unit I vector, and then plus 4 times the unit j vector, or the unit y vector. Or you could just write that as 4j. Right? This, you don't have to write this at all. What's the initial velocity? Well, the initial velocity, so it has magnitude of 120 feet per second. It's at a 30-degree angle. So what's its x component? Let me do this in a different color. What's the x component? The x component would be this vector right here. Well, it would be 120 times the cosine of 30 degrees, right? And you can review the trigonometry or review even the early projectile motion problems to get that. 120 cosine 30 degrees. And we'll multiply that times I. And then what's the y component? Well, that's just 120 sine of 30 degrees. Plus, let me do it in a different color, just for variety. Plus 120 sine of 30 degrees j. Right? That's its component in the y direction. And let's see, so we can rewrite the initial velocity. What's cosine of 30 degrees? It's square root of 3 over 2, right? So square root of 3 over, this is square root of 3 over 2. Square root of 3 over 2. Square root of 3 over 2 times 120, that's 60 square roots of 3. 60 square roots of 3, and that's times the x unit vector, which we denote by I with a little funny hat on top. I'm going to switch colors again just so I don't get all messy. Plus, I shouldn't use that color because I was plus, I like to keep it colorful. What's sine of 30 degrees? Well, that's 1/2. So 1/2 times 120, so that's 60j. Okay, so we figured out what the initial position vector is. We know what the initial velocity vector is. What's the acceleration vector? Well, what's the only force acting on this problem after we've hit the ball? Well, the only force is gravity. And since we're dealing with the English system, how fast does anything accelerate on Earth with gravity? Well, the acceleration vector just pulls down, right? This is the acceleration vector. It just pulls down at 32 feet per second squared, right? So the acceleration vector once again, it has no x component, just like the position vector had. 0 times x. And it's pulling down, so its y component is negative, minus 32j. Or we could just write this as minus 32j. So we've solved for, we know all of the different vectors in this equation. Let's fill them in. So now we know, I'm going to switch colors again to the position. And this is neat because now we're going to be able to figure out the x and y position of the ball at any given time t. The position as a function of t. And this is neat. This is a vector as a function of time. The initial position, well, the initial position we just said was just 4j. Right? It only has a y component. Equals 4j plus the initial velocity times time. So plus, or I could say time times the initial velocity. What's the initial velocity? 60 square roots of 3I. This is t right here. 60 square roots of 3I. And then plus 60j. Right? This was that's this I just filled in times time. That's where I got, right? Because initial velocity times time. And then plus, I'll take the t squared over 2 out front. T squared over 2 times the acceleration vector. Well, what's the acceleration vector? Well, that's just minus 32j. So minus 32j, right, where j is the unit vector in the y direction. And let's simplify it. That equals 4j plus, distribute this time, 60 square roots of 3ti plus 60tj, and then 1/2 times minus 32 is minus 16, right? Minus 16. So you get minus 16t squared j. Oh, look, I'm actually run out of time, so I'll continue this in the next video. See you soon.